So we know that most ionic compounds are crystalline solids. They're going to have a definite crystal structure. In your descriptions of the things that you looked at in the lab today, what struck you? They were all real. I think you could have said, white crystals for all of them. They were all white or colorless. They were all, either granular or cubey or blocky or, crystalline. The descriptions didn't vary a whole lot. There were none that had a real sharp odor that was noticeable in the dry form. And what I'll tell you is that some of them were ionic compounds. Some were not. So when we do, and we talked about this briefly, we'll do a lot more with this next chapter and you probably did this in physical science, doing some basic formula writing. When you have two ionic compounds, or when you have an ionic compound, the formula, like in molecular formulas, it's the actual number of each kind of atom in a molecule. There are no molecules in ionic compounds. So this is just a ratio. That's all it is a ratio. And it's so that they balance out to be neutral. And like I said, we'll do a lot more with that next chapter. We did the Lewis dot diagrams, for instance. We showed sodium versus the sodium ion. Once it's given up its electron. We showed chlorine and the chlorine ion, I believe. And then copying that, whoops. And moving that. And remember, we always have to have ions in a bracket. So we saw those. This is where we hadn't quite gotten to. So they form, ionic compounds form these, it's a lattice. It's like if you imagine three-dimensional chicken wire or hardware cloth. It's like an actual framework, like a scaffold. And at each juncture point, you've got an atom. And we talked a little bit about, cutie pie and best friend and the rush of two things that are attractive to one another racing towards one another. That's a lot of energy until they hit a point where suddenly they're repelled by one another and they're forced backwards, which is also energy. So the crystal lattice is a setup where these atoms are stationary at the point where they're balanced, where the positive and negative charges are attracting one another and the positive and positive charges aren't repelling one another. So it's this real delicate balancing point. It's kind of like a high wire act. They're perched at the point where all of that energy is minimized, and it's all delicately balanced. So it tends to evenly space the positive and negative charges, and we don't look at bond energy the same way we did for molecular compounds. We talked about double and triple bonds and how they have more energy. We don't have the same kind of bonds here. These are not things that are interlocking fingers. They're just standing shoulder to shoulder. Instead of holding hands, they're doing knuckles. I don't know what the metaphor is. But we have to calculate the energy that's contained in that substance differently. It still has embodied energy. It still has this potential chemical energy. So we talk about it as lattice energy. And I don't, for the confines of a Chem 1 class at the high school level, I don't expect you to know much more about lattice energy than that it's sort of the corollary of bond energy, but in ionic compounds. The book definition is the energy released when 1 mole of an ionic crystalline compound is formed from gaseous ions. So if you've got sodium existing as a gas, and we can do that. If you have sodium existing as a gas and you have chlorine gas and you mix them, you've got gaseous ions. When they come together in the air, they're going to actually form sodium chloride. And I can show you a video of this. So the point of watching the popcorn get salted with fresh salt, and it doesn't matter if salt's fresh or not, is just that you can take gaseous ions and merge them in such a way that they become a crystalline ionic solid. When you do that, they're more stable. And so there's energy released to the environment. If you remember our little diagram with, where did the energy go, in essence. So if their energy level is here, and they're kind of unstable and kind of high energy when they're gaseous ions, and when they're joined, their energy level is here, then that amount of energy is given off to the environment. So that difference in their high unstable energy and their lower, more stable energy once they formed a crystalline solid is the lattice energy. So like I said, I don't expect you to know a whole lot about it, other than it's similar to bond energy, but it applies only to ionic compounds. Okay, this is the real nuts and bolts for today, isn't it? So when we have a molecular compound, remember that inside each molecule, those things are actually physically interlocked. They are actually sort of holding hands. Their electron clouds are overlapping, and they're connected. So the bonds inside the molecule are very, very strong. But in between two molecules of a molecular compound, we just have what are called intermolecular forces. And they're not particularly strong, except in a few sort of exceptions. In an ionic compound, you've got all these positive and negative ions shoulder to shoulder. So I'm going to draw something here for you. 1, 2, 3, 4, 5, 6. So this is just sugar. This is a very bad drawing of a very generalized sugar molecule. But it's, the idea being that it's a molecule, and those carbon and, oops, I forgot my oxygens, didn't I? I'll stick a few oxygens in here. Good enough, good enough. Those carbons and oxygens and hydrogens are actually sharing electrons. So they're very, very strongly bonded. But this sugar molecule sitting up against another sugar molecule, it doesn't take too much energy to get them to move apart. So when they're in a solid form, they're kind of rigidly locked in position. You've seen sugar, you saw sucrose today. They're locked geometrically. They form crystals. But if we take some energy, say heat them with a little candle flame, we can get these to move apart. And if they move apart and they start to slide past one another, what have we done with it? What have we done with it? We've melted it. Yeah. And I believe you might have some experience melting sugar. Yes? Yeah. And that's because the forces between the individual molecules are not particularly strong. So adding energy to it, just from a candle flame, is enough to break the bonds between the molecules, to break the intermolecular forces, to overcome them and get them to move apart and become a liquid and stop being a solid. If we have an ionic, so this was a molecular compound. If we have an ionic compound, things are a little bit different. So let's take sodium chloride, everybody's favorite molecular or ionic compound. Jeez Louise. Okay, so we've got our sodium chloride here, and sodium chloride is this lattice of positive and negative charges. And every single negative charge is attracted to every single positive charge near it, and every single positive charge is attracted to every single negative charge near it. So it's really this huge mass of attraction. So within something like this lovely chunk of salt here, you've got forces of attraction running in all directions. This is three-dimensional. I mean, I'm showing it two-dimensionally because that's kind of the limits of what I can do. But those are some pretty powerful forces of attraction. So when we attempt to heat this thing up with a candle flame, you can't get these, you can't overcome that level of attraction with the amount of energy possible from a candle. Can you melt salt? Yes, you can. But you're not going to do it in a lab. You're not going to do it here because it's going to take, what is it, like 800 Celsius? I think it's a couple thousand degrees Fahrenheit. You're not going to do it in your oven at home. So they make those salt masks. If you were looking for a gift, a birthday or Mother's Day gift, or for an auntie or grandma or mom or sister or somebody who needs some kind of like little pampering relaxation gift, they sell salt masks, and it's a bag. You can make it yourself. It's a fabric bag filled with salt, and you put it in the microwave, and it gets really hot, and the salt holds the heat, and then you can lay it on your face and lay there, and nobody bothers you. It looks very serious. Why can you do that with salt? Because it's not going to melt. What would happen if you did it with sugar? It would be disgusting. It would be a gooey mess, and you would probably burn the person who you love so much and wanted to give a nice relaxation gift to's face, and that would not be the kind of gift you were intending, I think. So don't make a sugar mask. Make a salt mask. Phenyl salicylate mask. Would that work? No, not so much. The forces of attraction in an ionic compound run through the whole material. And that gives it some really interesting properties. Also, don't forget that these are ions. So, what do we see in ionic and molecular compounds? Ionics tend to have much higher melting points. So which three substances in your lab today do you think were ionic? Calcium chloride, potassium iodide, calcium chloride. Now, from your experience, from knowing what kinds of substances bond ionically based on electronegativity differences, we talk a lot about, sometimes we talk about East Coast, West Coast marriages. So, group 1 and group 17, yeah, that's going to be ionic. Group 2 and group 16 or 17, that's going to be ionic. Potassium iodide, what groups are we talking about? You can look at a periodic table. I don't expect you to have this memorized. What kind of bond would you predict for those two? Potassium iodide? Potassium? Ionic, yeah. Because potassium is group 1, iodine is group 17. We would certainly expect that those would form an ionic bond. Well, and experimentally, has what you've seen so far done anything to make you think that they wouldn't be bonded ionically? No, you couldn't melt them at lab temperatures. So that kind of, based on this information, that would tend to support the hypothesis that these things have an ionic bond. Ionic compounds tend to be really hard, but they tend to be brittle. What did we say about metals? They're malleable, right? And when we talked about molecular compounds, they have varying levels of hardness. Diamonds are a molecular compound. That's carbon bonded to itself molecularly. It's sharing electrons. What do we know about diamond? What do we know about diamonds? What's the primary use of diamonds on this planet? Nope. What? No. What do we use diamonds for most? It's not for their pretty. It's to cut with. Diamond saws. Diamond drill bits. Diamonds are the hardest substance known. So we tend to use diamonds to cut other things. You can go out and get, and industrial diamonds are not sparkly or pretty. They're just hard as, diamonds. And they're just grit. It looks like the sand on sandpaper, except it's made of diamonds. The sand on sandpaper is typically silicon dioxide or some other thing, which is a molecular compound. Pretty hard, but also fairly resistant to breaking down. You can't smash a diamond with a hammer. They're not that brittle. With ionic compounds, here's the interesting thing. So if we get rid of these little red arrows, if we've got an ionic compound like this, we said that, you know, the forces of attraction in between all these things are tremendous. What happens, I'm going to move this entire thing down a little bit. What happens if I come along with a big hammer? You'll just have to believe that this is the front part of my big hammer. And I hit this so that this entire thing shifts like this. What happens to the forces of attraction in the substance? Have they changed? Now it's repellent. So now this thing is actually going to just split. Because now instead of a force of attraction here, you have a force of repulsion, and this thing is going to split right off. So ionic compounds tend to be brittle because their internal strength, their hardness, is completely reliant on all of those ions being lined up correctly. If you shift that lineup, they just split. Let's demonstrate this. Okay, and I guess there are a limited number of years in which I can continue to do the shattering salt. Now, I'm not going to ever shatter my big, beautiful one there because that's got a nice clear, that was my muddy sample, so I'm okay with hitting my muddy sample with a hammer. That one's my prize. If you ever get a chance to go to the salt mines under Lake Erie, do it. They only do it for educational field trips. Typically like geology classes. I went with a geology class from YSU, and they only allow, there's a limit, I don't know if it's like 12 or 15 people in on a group, and I mean it's a working mine, so they don't want people in their way. So it's very controlled. They don't do like public tours or anything, but if you ever get a chance to go to a salt mine, it is awesome. It is so cool. You should do it. And they let us take samples out. You could bring a bag and take as many samples as you could carry. So, okay. So that though is why ionic compounds tend to be brittle. Now, the part that we're going to get to tomorrow when we have the conductivity apparatus is this. Ionic compounds tend to be conductive. Ionic compounds tend to be conductive when dissolved in water. So, without talking too much yet about why that is, I want to talk about what happens when we put an ionic compound into water. So, if I take this chunk of virtual salt and I put it into water, there's all the water. Remember that water is what kind of molecule? What kind of bond does water have? Hydrogen and oxygen. We've got our little Mickey with his little positive ears, whoops, and his little negative chin. Ring a bell? Covalent. It's covalent, but it's polar or nonpolar? Polar. It's a polar covalent compound. So it's got some areas of partial charge. What that allows the water to do is to snake in between all of these ions and separate them. And what actually happens, and we will talk a lot about this in chapter 13, and it's cool stuff. What happens is you end up with, instead of salt in your water, you end up with sodium ions and chlorine ions in your water. They're free, they're loose. They're not connected to one another anymore. We call it dissolution. They dissolve, they dissociate into their respective ions. Well, what do you know about electricity? What is electricity? I know it's Monday. It's hard. What's electric? Electricity. What is it? There's a song called Electricity and All. Very old. Anyway. It's the movement of Electrons! Yeah, that's all it is. It's just electrons moving from one place to another. Well, if you've got a bunch of ions free in the water, guess what? You now have a ready source of electrons that move. So ionic compounds, when dissolved in water, tend to conduct electricity. Here's something I'm going to tell you. How many of you have heard that you should not swim in a lightning storm? What I'm going to tell you is that if you had a pool or a vessel of some sort full of distilled water, you could swim to your heart's content. Distilled water is pretty non-conductive. It's not the water that conducts electricity. It's the stuff in it. So we'll stop there, but I'll tell you a brief story to talk about this idea that ionic compounds dissolved in water conduct electricity. So years ago in another life, I worked for the Division of Wildlife in the Fisheries Division. This was right out of college. I was getting like, $8 an hour, which at the time was almost twice minimum wage. Woo! And as the low person on the totem pole, I got to do the unpleasant ends of just about everything we did. And what the Fisheries Division does is a lot of fish sampling. So we collected eggs and sperm from fish. We did what's called, we did walleye survey. We did muskie survey. We also did what's called electrofishing. Has anybody here ever touched a shorted out cord or an electric fence? Ooh, okay. What happens to your muscles when you get shocked? Yeah, they freeze up. That's why they always say, you should never test an electric fence with the open side of your hand, because if it's live, your hand will close on the fence, and there's really no way to get off at that point. So you always test a fence with the back of your hand, so that if your hand seizes, it goes this way. Well, the same applies to fish. And so electronight fishing involves taking out a boat. There's a very badly drawn boat. And on that boat is a big boom that hangs out over the water. And attached to that boom, and it's flat, but I'm drawing it so that you can see what it is this double loop of heavy tubing, metal tubing. This is all metal. And, oops. So we'll just show a single loop for simplicity. Hanging off of that loop are a bunch of electrodes, and they're on little like alligator clips, and you hook them onto the tube, and there is a person standing up here with a net, and they've got their foot on a pedal. And as long as they are pushing that pedal down, electricity is flowing out through that boom, through this tube, and down into the electrodes, and it creates an electrical field in the water. And when fish swim into that electrical field, guess what happens? Their muscles seize up, and they're frozen. And it doesn't, for the most part, it doesn't kill them. Really tiny little fish, if they swim into the field, will sometimes just get fried. But when we did electronight fishing, we were primarily interested in bluegill and bass. This was a bluegill bass survey, and I did this one down in Atwood. So the person who's standing up there with their foot on the pedal, and there are usually two of you, with the big long net, as you see fish enter the field, you scoop them up. Once they spasm and freeze, you scoop them, and if they're your target species, you've got a well. It's like a big tub of water on the boat. You put the target species in, and you'll go 100 yards and then stop, do what you need to do, release all the fish, and then keep going. And so you're weighing, measuring, taking a scale sample, and it's the idea for wildlife management is that you get a sense of what the fish population is like, and what management needs to happen. Well, the interesting part is that before you set out every night, and you do this at night, you get on the lake at dusk. It's really kind of neat because you're out on the water at night. You don't get to do that very often. You would take what's called a Secchi disk reading. So here's the surface of the water. A Secchi disk is a black and white disk. It looks like this. It's on a chain or a rope. And some of you may have seen something like this. Has anybody ever seen a Secchi disk? So you stand at on the boat and you drop the disc down into the water and you measure, there are marks on the rope or the chain, you measure how far down in the water you have to go before you can no longer see the difference between the black and white. So you're measuring how far down light is traveling in the water. And the biologist will say, okay, you say 2.3 feet. Okay. And then the biologist will look it up on a chart and he'll go, or she'll go, or whoever, it was a guy when I was doing it, 10 electrodes. Okay. And the next night you might be out on a different lake and you say, 5.6 feet. Wow, that's really clear. 18 electrodes. The clearer the water, the more electrodes. Why? The clearer, there's not as much stuff in it. The clearer the water, the fewer dissolved compounds are in that lake. And the fewer dissolved compounds are in that lake, the less conductive the lake water is. The less conductive it is, the more electricity you're going to have to deliver to generate the same size of field. So, if that water is super cloudy, like after a rain, there are a lot, realize that salts wash out of the soil. There are calcium and potassium and sodium ions in the soil. They wash out. The more dissolved solids you have in that body of water, the more conductive it is, the less current you need to put into the water to generate the kind of field you need to shock the fish. And the goal is to shock them without killing them. So just a little bit of a real-world application of this idea. So in retrospect, ionic compounds tend to be conductive. Tomorrow when we have the conductivity apparatus, and you'll be so impressed with how complicated and exciting it is. That's sarcasm, obviously. Based on what you've seen so far with melting point, you might be able to make a pretty good guess about what you think will conduct electricity. So, okay, we'll pick up tomorrow with the ethanol and the conductivity. That's it.